Welcome, everybody. Welcome to ARC404, Metering the Hybrid Cloud. My name is Dan Garrity, and I'm here with my colleague, Jack Chen. We're from the AWS Commerce Platform. I'll tell you a little bit more about that in a second. We're going to talk to you about ways that you can use AWS tools and some of your own grit and muscle to build out systems that can help you meter from your on-prem and other cloud providers into AWS. We're going to take questions at the end. We'll just be down here in front, so rather than doing the microphones and all that, we'll be available at the end. So if you have questions, if you could hold them until the end, I'd appreciate it. So, really excited to be here talking to you about this. This is a kind of a perennial customer ask, and so we're excited to share some of what we've learned. I want to make it clear that we are not talking about a public service that we have to offer. Instead, what we're going to do is talk to you about the hard lessons that we've learned and talk to you about the AWS tools that you can use to put together to accomplish what we accomplish in the metering pipeline. So I'll give you a little background, what the problem is, what we're trying to solve. We can talk about some alternatives for building this using commercially available tools. Then I'm going to turn it over to Jack. He's going to tell you how you could build such a system, and then we'll circle back and talk about what the benefits of this would be. Now, just before we get started a little bit, if I had to divide the world between finance people and engineers, if I forced you to make a decision, because I know a lot of you are here because you cover both avenues, how many would say you're principally financially oriented? Okay. And the rest, I'm presuming, are more engineering oriented? Okay, well, we have a nice mix here. So we're gonna explain this in ways that hopefully both sides can understand. So the Commerce Platform, first, let me just say, we're the people that are responsible effectively for generating your bill. Jack and I work at the very front end of that process, so we're the ones that do all the metering from the service teams, from EC2 and S3 and RDS. They send their information on usage into us. We compile it, rate it, produce the bills, and things like that. You see the bills and the data, the usage data that we provide in a variety of artifacts, like, for example, the billing console, the cost explorer, AWS budgets, and something that's relatively new, the cost and usage reports. How many of you have ever been on the AWS console? Okay, yes, I am just checking to see if everybody's awake, because most of you have probably been there. Okay, what about, how many of you have created a budget? Okay, good. And how many of you have looked at a cost and usage report? Wow, that's fantastic. Okay, great. Well, I know that the AWS bill is often the subject of a number of, I guess, jokes. It's been said that you need a PhD to understand your bill from AWS, and the only remaining question is a PhD in what discipline? We're not exactly sure. It is challenging, but part of the reason that it's challenging is because our job is to liberate you from your fixed infrastructure, from your data centers and your other providers, allow you to effectively make the move to the cloud. And things are different in the cloud, and you need to have information, detailed information about what's going on with your infrastructure in the cloud. And so that's why we provide this extremely rich data. It can be a lot, but our customers, every time we go and we say, okay, well, we can simplify this, cut this down by an order of magnitude, we'll just eliminate this piece of detail. That's not something that our customers want. They want to understand what's happening in their infrastructure. And that's kind of the basis of this talk. We've realized that people really want to understand what's going on in their AWS infrastructure. And we have some tools to say, well, let's get that same usage infrastructure, that same understanding for our on-prem and for our infrastructure and other cloud providers. So the Cost Explorer is our graphical visual user interface that allows you to understand what's going on usage-wise in your bill and cost, both cost and usage. It's meant for human consumption. You go in there through the website, you're selecting filters and interacting with the information as a human. We have various levels of reports all the way down to the cost and usage report, which many of you are familiar with, which I'm very happy about. This is our most detailed data possible. I think it's probably the most granular usage data maybe on the planet. I don't know. It's down to an hourly level with resource IDs, tells you which RIs are covering which instances. It's very sophisticated. That's meant for programmatic consumption. Like, we're not really expecting anybody to read that cost and usage report. But that's the range of services that we provide. So human readable in the Cost Explorer, machine readable at the cost and usage report. The details matter. We're providing a rich set of data because customers really want that. So we're going to talk today about how we can provide that kind of data for the on-prem environment. Because really, irrespective of where you consume resources, whether it's on-prem or in Azure or AWS, your shareholders need you to account for them, for those resources properly. And in the data center days, a lot of that was about efficiency. It was about asset utilization. You know, if you have a bunch of expensive assets, really, what you really want to measure is how effectively are you utilizing those assets. You just don't want them to be idle. So we used to measure things in the data center like efficiency. You know, what is my average percent CPU utilization? Or what's my disk utilization or my storage utilization? What's my I/O bandwidth utilization? I call that efficiency. And one of the first things that happens when you move from an on-prem into the cloud is that concept gets turned a little bit sideways, and I call it effectiveness. So what we really want to do is manage effectiveness versus efficiency. And of course, I'm not at all saying that percent CPU utilization doesn't matter, because of course it still does. But because of the benefits of the cloud, because of the elasticity that you have, and the fact that you're only paying for what you use, the efficiency is dominated really by a measure that we call effectiveness. So how can you manage the effectiveness of your implementation wherever it lives? The first thing you have to have is access to the data. The right people need to be able to effortlessly access the data they need to make decisions about their use of technology. We're just talking about this, obviously, a bunch of meetings with customers here at reInvent. And this concept of getting the usage data from these reports back to the person that spun up the instance so that person can see what's happening is crucial. So you have to get access to the information. The information needs to be understandable. This is an area where we, as the Commerce Platform, have made some strides recently. We have a long ways to go because the data is complex. Part of that is because our services are complex. We have a multitude of different offerings. If you just look in the compute category, for example, EC2, we've got RIs, we have convertibles, and so forth. Those offerings have to be expressed in the bill. So we can make a crystal clear representation of what's in the bill, and it still looks complicated because it is. But you have to be able to understand it. That's where the data, the quality of the data and the way it's organized comes into play. Once you have access to the data and you can understand it, then you need to put controls around it. And when I talk about control here, I'm talking to the finance, those people that raise their hands, talking about financial controls, the ability to audit, to understand what the usage is. It's like in the old days you could walk through the data center and count asset tags. Well, now you have to walk through a virtual data center counting usage tags. There is really no analog. And so that control allows you to examine, inspect, and audit your usage. The next step is once you've got your controls in place and you've got your data, you can understand it, your controls are in place, now you want to optimize your infrastructure. And this is a place where we have a lot of tools, a trusted advisor. We just recently in the Cost Explorer just a week ago introduced RI recommendations. So we'll go back over time, analyze your usage, and put forth some recommendations so you can save money. And once you've optimized your infrastructure, then typically most companies, most of you, have to find a way to allocate those costs back to their original cost centers. There's differences between the way that you accomplish those 5 things in the cloud versus the way that you accomplish those 5 things on-prem is slightly different. There is, in the traditional infrastructure, there are a number of players that help you allocate different pieces of hardware, different pieces of software, personnel costs, for example, Apptio. Many of you may use that in the cloud, or sorry, in your own data center. There's a lot of existing tools that play there. In the fullness of time, we believe that the vast majority of companies are going to move most of their workloads into the cloud, whether it's ours or another provider. And it is, and always will be, a priority for us to make to allow you to run on AWS as if it were a seamless extension of your own data center. Because, unless you're all in AWS from the outset, like born in the cloud, let's face it, pretty much everyone is in some kind of a hybrid environment. So I just want to look at a couple of these key differences that drive differences in the way we measure what we're doing in these different environments. So first of all, of course, the cloud is pay-as-you-go. So instead of having a bunch of fixed infrastructure, now you've got elasticity, and your payload is growing and shrinking. That's pretty much the opposite of, well, typically of a data center, unless you're running your own private cloud with VMware or something similar. Transactions are much more detailed. They're billed at the hour, the second, the call, per million calls. It's much finer-grained transactions, rather than once a quarter making a call or executing a purchase order and buying a bunch of equipment for the data center. And costs that are tied to departments at the time of purchase now are floating around and need to be attributed back in the chargeback process. So really what we're doing is we're going from a CapEx world to an OpEx world. We're going from asset tags to usage data. We're going from machines to looking at APIs. And we're going from recurring subscriptions to usage-based costing. We're doing a lot of this for you in the AWS cloud. Once you get accustomed to this and get familiar with it and comfortable with it, it's a good way to measure your costs. What we're trying to do here is say, hey, how can we take that methodology, usage-based accounting, and take it and move it to on-prem? And that's what Jack's going to tell you about as soon as I click through these next few slides. So we've gone from counting assets to measuring usage. And in doing so, we're creating some simple requirements. And the question that we're asking is, who's using how much of my infrastructure? And I guess I should have put on there, and when. And what we're going to do is I'm just going to introduce this concept of a metering record, which is just a simple, small, compact piece of data, packet of data that contains essentially an account ID, a user ID, an operation type, and a value. And this metering record is what's going to get beamed around throughout this system that Jack's going to talk about. We're going to have a lot of these metering records, and they need to be secure. They need to come in on an authenticated endpoint. We need to make sure that not only are you who you say you are, but also that you have the right, have the authorization to execute this registering of this metered usage. So security, always our number one priority, and obviously that's going to be included in what Jack talks about, but the scale. So I just want to point out some of the lessons that we've learned. You can imagine we're sending these metering records in, and we grow by the cube of the number of customers AWS has, by the number of products AWS has, by the amount of usage AWS has. So we're dealing with tremendous scale, and a lot of what he's talking about is going to talk to you about how to deal with scale. Also aggregation, because you're not going to want to look at every single millisecond you're going to want to be able to aggregate these, and you're going to want to do that on the edge. So he's going to talk about that. And then, of course, accuracy is extremely important. Some of the things that we have to do in our systems, in our design, in our architecture, is account for exactly once delivery. And as you know, in a distributed system, that's not always easy. You can get maybe at least once, or most of the time, but getting it exactly once is a challenge. So he'll talk about that. So applications are what businesses run. So I recognize from an engineering perspective or from a data center perspective, we talk about instances and assets and disks and these kinds of things. But really, at the end of the day, you want to measure your applications. And applications are made up of workloads. And as the business moves into the cloud, we typically see some patterns where they move first with the brand new application that has no dependencies. But then as you start to move the rest of your applications, you kind of have to ask the question, well, which ones should we move first, and how fast should we move these? And that's where I think this kind of analysis will be applicable, helping you understand which applications are the ones to move first. Then you can build your cloud infrastructure workload by workload. Yeah, so Jim Collins, he's a famous author that has been quoted by our esteemed leader, Jeff Bezos, many times because of the flywheel concept. But he wrote a book called Built to Last. And it was lauded as a great business book about how to build an enduring business. But it really started with startups. And it's like, if you're born in the cloud, you can build an enduring infrastructure from the get-go. It's much harder to do that when you're born in a data center and you're moving in. So that's our goal, help you figure out what to move first. The other thing that's important is to have an integrated view. AWS, we have a bunch of tools that shows you what's going on within AWS. You may have other tools on-prem. You may be trying to move those tools from the on-prem environment into AWS. Sometimes that's great and that works. If people have homegrown applications or they're running agents, user agents, these kinds of things, those are a little bit harder to move to the cloud. But ultimately, at the end of the day, we're going to want to have an integrated view of this. And so one of the things that we'll talk about at the end is how you can take the cost and usage report data, put it into, for example, a Redshift cluster, and then add your own on-prem data in a similar schema so that you can have an integrated view. So then these become the final list of requirements. We talked about security, scale, aggregation, exactly once delivery. Should have mentioned that all of this stuff is multi-tenant, and this is because when you're moving enterprise applications, they're going to be multi-tenant. You're going to have multiple users using the same API or multiple accounts using the same database or multiple, whatever it is, they're all interleaved. And so a lot of what Jack is going to talk about is how to demux all of these multi-tenant users. So it's got to be multi-tenant, and it has to be integrated. So now that we've set up the requirements, I guess the question is how do we do something like this? And so I'm going to turn it over to Jack and let him talk to you about putting it in place.
Thank you, Dan. In order to answer Dan's question about who is using what of how much of my IT infrastructure, we need to first understand the different types of things that we are measuring. This really comes down to three different things that you can meter. There's the physical infrastructure, which includes your servers, your databases, your instances and containers, as well as the applications that are deployed across this infrastructure, and their utilization, resource, CPU, bandwidth, and so on. Finally, we get down to the level of services and APIs, which tracks the per user, per request level of access, the usage level access of your applications and services. Your architecture and the choice of technology that you use will vary dramatically based on what it is that you are measuring. From a scaling perspective, your physical infrastructure can often run in the thousands or hundreds of thousands of servers and instances that you measure, and the applications that are deployed across that, again, on the order of hundreds or thousands. In aggregate, this is a fairly large number, but as Dan mentioned, because this is something where you're tracking the total assets of your inventory, it's something that can be done over a longer period of time, typically on days, months, or even over quarters. However, when you make the change, to usage-based metering, you hit a different inflection of scale that's much, much larger. You are now looking at millions of requests, possibly hundreds of millions of requests per second that's touching your applications. And between these different things, you also get different information. Again, with physical infrastructure, with the assets of and catalog of applications that you run, you're really looking at what it is that you have deployed. You can understand better efficiencies by identifying those servers or those instances that are underperforming and sort of reallocating them to some other purpose. With application-based or usage-based metering, you're really looking at the effectiveness of your business. This is where you can figure out how to invest your infrastructure into places that are that have more users or more activity. And this is how you really gain those kind of insights. So with that in mind, let's take a deeper dive into building a system that actually supports usage-based metering. This is where really the scale comes in, and that's where the fun comes in. There's a lot of different components that make up sort of a metering pipeline that you would have to build, but I'm going to focus on sort of 3 different areas around collection, processing, and auditing. This is where really the most interesting and most challenging problems occur at scale, and we're going to talk about some of the things and some of the solutions that we have learned along the way to help you deal with that. First, when you collect the usage data, you really are focusing on getting the data off of the different hosts and instances, containers, as quickly off of the edge as possible into a central place. And this is where you need to handle that scale to be able to deal with the fire hose of data that's coming in. You also want to make a decision around building indexes to make it simpler downstream when you do your processing, so that when you're processing your data in a multi-tenant system, you only pull down the data that you need instead of pulling down the entire world. And this is also where we want to make some early decisions around exactly once processing. We want to make sure that we have the right semantics in place so that we can actually support exactly once processing and auditing throughout our pipeline. In the processing stage, we're really talking about aggregation in this particular conversation, but you can imagine applying other kinds of transformations in the processing pipeline. And again, we want to make sure that we are supporting a multi-tenant type of environment. And finally, with auditing and verification, we're really talking about tracking the accuracy, the completeness and correctness of the data that's going through your pipeline. And we're going to talk a little bit more about the different ways in which you can do this. Just to better set expectations, we're going to spend the majority of our time in the initial collection area. This is because from the lessons that we have learned at AWS, what we find is that when you make decisions early in the pipeline, it's really, again, it simplifies your workflow throughout the entirety of your systems. It makes it more resilient, more flexible, and it ultimately makes it more scalable. So with that, let's focus on collecting usage data. This is a system view of the architecture that we have. Again, we want to focus on getting the data off of the edge as quickly as possible. So in this case, we have you can use the ELB load balancer where the batches of metering records are coming in, and you can set it through the collection stage. You're going through an authorization layer, and you're building a scalable, horizontally scaled system to be able to collect this data. This is also where we want to perform some simple validation. You might want to do some schema formatting validation before you offload the data into a persistent data store. Here, we take the data, we put it into S3, and we put references to it in DynamoDB. This is also where you can make an early decision, architectural decision about trade-offs between streaming versus batch. Now, streaming makes it easier for your clients, for your customers, to put records directly into a streaming pipeline and pass it to the rest of the system. However, from our experience, streaming, in order to guarantee exactly one's processing, streaming in a streaming platform, you have to build a lot more complicated tools to be able to support that. And so our objective here is to get the data off the edge as quickly as possible. So using a batch-based system is actually dead simple, and it allows you to scale out and support exactly one semantics a lot simpler. And this is the reason we suggest to use that approach instead. Once you get the data into the pipeline, we then pass it through an SQSQ to go to a local aggregation stage. Now, this is an optional stage. And the reason why it's optional is anytime you introduce another component or another system in a distributed environment, you're adding more complexity, more opportunities for failures, more opportunity for duplicate data that has to be retransmitted. But what we have found is that there's actually a lot of benefits with doing some simple local aggregation within a batch of metering records. And the reason why that is when you get to API or service level metering, you tend to see a lot of repetitive actions. The same user making the same call to the same product multiple times can give you great efficiencies when you reduce that data, often up to 10x. And that's the reason why we want to add this kind of local aggregation stage in. Now, with this benefit, you may ask the question, if you get this efficiency, why not push it further up the stack? You can put it as close to the edge as possible. From our experience, that's the trade-off of CPU that you have at the edge versus the bandwidth. It's much better to just get the data off because you really want to reserve that CPU to serve the applications for your users doing whatever it is that you're doing. So pushing that data further down is a better trade-off. Similarly, in the collection stage, if you do aggregation within your batch, at that stage, you lose the resolution. Once you aggregate over the information, that detail is gone. And what we find is that there are times when you want to go back and sort of really get to that detailed level view of information for auditing, for sort of a detailed check. And it's better to get the data, offload it, and then do your aggregation a further step. Finally, from the aggregation stage, we then route our traffic to an indexing stage. This is where we start introducing more state into our system by introducing partitions in terms of how you build your index. And this is where a lot of the complexity really comes in. And we're using Kinesis in this example to sort of act as a streaming map reduce. So in my next few slides, I'm going to focus on sort of dealing with some of the complexity that comes in when this hits scale. This is a few examples of some of the metering records that you can generate. In this case, it's a pretty simple schema. There's a user ID, an application, an operation that's executed, a time, as well as the value, the number of things that were run. And as you can see, in a multi-tenant system, you have users that submit applications across different types of batches of records. And so in order to build an index, you can imagine that for every user, in every batch that exists, you have to create sort of this product of records together. And in this particular case, the cardinality, or the big O, is an n times m type of operation, where n is the number of users you have, and m is the number of batches that those user records exist. And this becomes a big challenge in using, say, DynamoDB as a persistent layer to store the number of IOPS that you have to handle to deal with to build this index. And anytime you add a new dimension, say that you want to track the applications that are deployed across your batches, this again introduces another O of n times m type of operation to store the number of IOPS, to track the number of IOPS that you need to be able to store this index. So in order to control this scale, you really need to introduce sort of a map reduce-like function to be able to collect similar things together. So in this case, for our user index, you can imagine putting the different user data together in order to generate a larger list of batches before you write them into your database. This effectively reduces your throughput requirements from an O of n times m operation to an O of n operation. Now, it's not exactly like that because depending on how large that list of writes, how large that list of batches get, you may incur multiple writes into, say, DynamoDB. But this is where sort of Kinesis comes in as a streaming map to really buffer and allow you to sort of dial up and down how frequently you write into your database. You can imagine that the longer you buffer your input, the fewer writes that you have to do. Some additional other benefits of using Kinesis as a streaming map. Deduplication is handled locally. Again, in an exactly one system, we really want to focus on making sure that retransmits that happen in the pipeline, either user-generated or system-generated, are deduped throughout in our system. In this case, with a streaming map, you know that every batch for a particular index is going to the same place so that you can handle dedupe locally in memory without sort of incurring a costly distributed systems or a costly global data store. Please note that this is actually not something that comes for free with Kinesis, so you do have to build some tooling, build some systems to support that, but what we find is that it's actually fairly straightforward to do. The map workloads, in this case, also reduce the blast radius of failures in your system. So bad data or bad hosts will only impact a few partitions where they get mapped into your system so that the rest of the data can flow through without impacting everybody else. And ultimately, Kinesis provides streaming checkpointing semantics that allows you to incrementally progress along the way so that depending on how long you can buffer your input for about 10 minutes. And then when you checkpoint, if something fails along the way, you only lose that 10 minutes worth of processing before you have to come back. And introducing a map reduce, however, does add the possibility that you're going to hit hotspots. Now you're entering constraints within your partition. So for Kinesis, in Kinesis, for example, within a regular shard, we're talking about 1,000 TPS with 1 megabyte per second, and you can hit those pretty quickly for large enough indexes. So now we want to think about how do we actually deal with managing the hot partition. Here's a really simple example. Imagine you only have 2 partitions where all of the load is not evenly distributed, where one partition has 3 times as much as another, and you now have a very unbalanced load. So using Kinesis, the way that we sort of control this, the hotspots is by adding a little bit of entropy in terms of how we put the data into our system. In this case, Kinesis uses a partition key before it puts records into the stream. By adding a little bit of entropy, we can now sort of control the throughput and how many partitions, logical partitions we actually use within Kinesis. We recommend using some hash function over the field or fields that you are actually using to build your index. In this case, we're using a user ID, performing the hash over the user ID, and then mod it by some subpartition size. Subpartition size here is just a logical partition, and this is really what you use to sort of control the scale in the stream, right? The more subpartitions you want, the more logical partitions, the more even you want to spread out your load, the higher the subpartition size number you want. And because we value exactly one semantics, there's some other constraints that we want to add in when we define the subpartition, this entropy. We want to make sure that the hash function that you're using is deterministic, so that generates an idempotent result upon every use. And also that subpartition size itself is actually versioned in a time series kind of way. The reason why this is important is, again, you can have retransmits in the pipeline, so you want to make sure that any retransmitted data is using the same partition scheme that it used upon the previous run, so that you don't get muddled. You don't get information that cross between different times. This is a simple way to do this is just use a timestamp. When you generate the batch, you can have a timestamp that's associated with the batch at the time of generation, and then the timestamp is used with the subpartition size, so that when you see a batch come in from a previous timestamp, you can find the correct version to use, and then provide that as the entropy. So in our toy example, with the introduction of a subpartition parameter, we have better, more uniform distribution of our load across the partitions. This is the component view of the systems that we can use to manage hot partitions. The producer, when it's putting records into Kinesis, gains different I/O statistics. It can record things like the throughput or the TPS that's seen at each partition. It can also record information from Kinesis in terms of throttles. The hotspot manager in turn reads that information from Dynamo. It's then able to make decisions proactively and reactively based on the trends of growth as well as the throttles that it sees from Kinesis. In turn makes decisions and writes the subpartition information back into Dynamo, and then the producer reads that information and uses that to put records into the streaming map. You can also use APIs that are offered directly through Kinesis, such as split shards and merge shards to sort of control how you grow the stream. What we found in practice, though, is using our own logical partition gives us more control, gives us more flexibility, and to really do targeted changes into our stream by growing only a subset of partitions so that we don't impact the rest of the stream. So to quickly recap, for the collection our usage data, we're really focusing on how to horizontally scale and how to cheaply and quickly get data off of the edge. And we talked about building an index that's able to support making decisions later on in your processing stage so that you're only selectively pulling down the data that you need when you process, and then making some decisions again around exactly one semantics early on. Next, we want to talk about your processing stage and the things that you want to build to be able to support a multi-tenant kind of environment. This is a system view of the architecture that we use to aggregate and transform data in our pipeline. In this case, the controller is where all of the different job requests are coming in, the multi-tenant kind of jobs where you're trying to track processing by user or by application or by region or by time. And this job's then tracked against a fleet of different EMR clusters. In this particular design, we actually recommend that you use multiple EMR clusters instead of a single large EMR cluster that you're scaling up and down by adding more hosts or adding larger hosts. And the reason, again, for doing something like this is just about building in resiliency. What we find is poison pills or bad data sometimes can take down an entire large cluster and take your processing pipeline to a screeching halt. And you really want to protect yourself against that. And building support for multiple clusters allow you to sort of isolate the blast radius for failures. It also has additional benefits. What we find is that when you have this information, you can experiment a lot more quickly. You want to build different indexes, different ways that you want to aggregate or transform your data. And with a multi sort of cluster setup, you can isolate those experiments in a small place using production data without having to sort of impact the rest of your services in other users that are using this application. This is the component view of how the cluster manager interacts with different systems. In this case, the controller and the cluster manager work in tandem to be able to handle autoscale. The controller, again, takes requests for different types of jobs that are running. It submits those requests and it looks into a data store, in this case DynamoDB, to find available clusters to lease and also in queues of those jobs and stores that information into DynamoDB. For those jobs that are mapped to a cluster, it talks to EMR directly and kicks off those jobs. The cluster manager, in turn, pulls that information from Dynamo so that it can identify trends on how long the jobs are running and how big is the backlog so that it can make decisions on whether or not to spin up new clusters or tear them down. The net result of this is that you've effectively turned your different EMR clusters into ephemeral resources that you can spin up and tear down, just like an EC2 instance. From a workflow perspective, again, because you want to support a multi-tenant kind of system with different types of jobs, you want to really isolate and treat the different types of jobs, their inputs as well as their outputs, independently. You want to store this information so that you can do this processing in different stages. And I'll tell you a little bit more about sort of what that means. Once you've identified the jobs, the list of jobs, and for particular invocation, you then want to query the index that you built in the collection stage to then identify all the input that you need for that particular job. Once you have that index, once you have the batches identified, you want to lock this information down so that you can go ahead and so that if you had to rerun and reprocess, you have the same data set that's used for a previous job. Again, this goes into idempotency and goes into sort of deterministic and deduplication behaviors that you want in your system. Once the input is set, you're going to kick off an EMR job and perform the processing, again, whether it's aggregation or any other types of transforms you want to do. You can go ahead and run it through, and that completes the workflow. The two benefits that I mentioned around sort of this idempotency, the reason why you want to lock the different stages of input down, is that with the locked data set, again, you have guaranteed idempotency. If the aggregation fails, somewhat time along the way, some point in the processing stage, you can go back and rerun it without fear of generating duplicate data. And with that idempotency guarantee, your consumers that read this information, because it's deterministic, the output, they know exactly what the output should be, they can build better deduplication reasoning behind when they consume that information. And another benefit of using sort of a fixed data set is that it drives predictability. Now, with this information, the cluster manager can actually do auto-scaling by knowing that with this fixed input, this is how long it will take to run, this is my backlog of work, this is how much throughput, how many clusters I need to use to be able to actually make sure I go through the backlog. To recap, in the processing stage, again, we're focusing on aggregation in a multi-tenant system and using a batch-driven MapReduce framework like EMR, again, using multiple EMR clusters. Finally, we're going to take a look at how you can build auditing into your pipeline. And auditing is a critical step to prove the accuracy in your system. In this case, inside the metering pipeline, there are really two different things that you're auditing for. There's completeness and correctness. Completeness answers the question, did I process everything that I received? And correctness answers the question, did I process everything accurately? For auditing for completeness, it's fairly straightforward. In an eventually consistent system, you basically have to wait for all the data to arrive after some period of time before you kick off your completeness audit. And in this case, you want to measure for some fixed time window, say all of the metering data that was submitted for a particular hour, after some fixed time interval, say 2 hours after the time has happened, to sort of track as your input space to see these are all the batches that were submitted. You can match that against the manifest you generated when you process the data to see how does this line up, and if there's anything that's missing, then you have an error and you can fail the audit there. By comparison, audit for correctness is much more complicated at scale. And this is really where, in order to do it efficiently, we need to be able to fail fast so that you can react quickly when an audit fails, and also be able to do it in an incremental fashion. And the way to do that is to add in hashes in your audits so that you're not doing a line-by-line comparison and really relying on the item potency semantics within your pipeline so that you can do this in an incremental fashion. And we're going to spend a little bit more time talking about how you can build this auditing for correctness in this pipeline. First, for auditing, we talk a little bit about a checksum. This formula here really just something that you can rely on to guarantee that when you perform some hash or some checksum on the raw data, that you can get the same results on the aggregated side. In our previous example for our usage records, for the 3 different usage records that we have, when we apply a checksum, we can gain information around the hashes and the checksum for the individual records themselves, as well as a hash for the overall batch. And at this point, you can perform an incremental check to verify that the records checksums, when they are added together, matches the batch as well. This gives you the first opportunity to perform an incremental audit. And sort of armed with that information, you can persist the checksums with the index as you're building the index. So for our example from before, for each of the user indexes you're generating, for each of the input batches, you have a corresponding checksum that matches that batch. And when you're in the compute stage, in the processing side, you pass that checksum along with as the source information so that when you get the aggregated result, you're really comparing the source checksums with the aggregated checksum to make sure that they're correct. And if they don't match, this is where you can fail quickly for that job so that you can go and see what's going on while everything else continues to run. And so that kind of concludes the different areas of building out a metering pipeline. And some key takeaways I hope to leave you with here is that in the collection stage, you're really focused on getting the usage data off of the edge as quickly as possible, and you want to build an index to be able to simplify your processing downstream. You're making some early decisions in this stage so that you can make the rest of your pipeline more flexible and more resilient. In the processing stage, it's important from our lessons to treat EMR clusters like ephemeral resources. You want to be able to spin them up and tear them down on an on-needed basis. This allows you to gain some. This allows you to really meet the multi-tenant requirements of your system. And finally, for auditing and verification, it's really about auditing quickly and building using checksums, as well as relying on the item potency guarantees in your pipeline to be able to do it in an incremental fashion. And with that, I'm going to turn it back over to Dan.
Great. Thanks, Jack. So I think you can see it's complicated work. To meet these requirements of scale and security and multi-tenant and exactly once delivery and accuracy is challenging. It's hard work, and I hope that these lessons that we put here can be valuable to you as you build out systems like this. That are essentially financially oriented, so they have to have this control, audit, exactly once type of behavior. I think if you were able to or did build this system for yourselves and connected it to your on-prem environment and ended up essentially with all of this usage-based metering data organized by any of the keys that you passed in originally, so organized by application ID, for example, organized by user ID, for example, or organized by resource type. However you want to do it, you now have the same usage level data on an hourly basis that you'd be able to get from running resources in the AWS cloud. So the idea now is what do you get? If you combine those two data sources, now you can compare your effectiveness on an apples-to-apples basis. You can see how applications are using resources in your own on-prem data center versus how they're using them in the cloud. And that way, you can prioritize which workloads, I guess I should say, if any, because I know there are some out there that can do things better in their own data center. So prioritize workloads that are optimal for moving into the cloud. That would be the benefit of doing this. I think, again, it would also give you the ability to access data about your own on-prem operation or your operation that you may have in a different cloud, a joint cloud or Microsoft Cloud, whatever the case may be. It allows you to understand what's happening on a per application or a per user basis. It allows you to provide controls, audits, financial controls, understanding what's going on. Allows you to optimize your spend because now you can understand what you're actually using, who's using what, where, why, and when. And ultimately, use that data that you have to allocate costs back to the rightful owners within your own organization. So with that, thank you. Jack and I will be here for a few minutes after the talk. If you have questions, we'd be delighted to take them. Thank you.